Okay. So I'm not using the personal computer at the beginning. I just put it to get ready. And now I just need to make an introduction to the next topic, because today I'm changing, like we say in Italian, we turn the page of the book, and I'm moving to a different topic, the next one. And the main issue is still to generate synthetic data for water resources estimation. So this is still the main issue that we are dealing with. And in the past few weeks, we dealt with application of rainfall runoff models to obtain synthetic data. And now we turn to, as I said, to a different technique. And basically, we consider a different technique because it's a different solution to solve the problem. And of course, this new solution has different behaviors and can be more practical in some situations. So basically, the previous solution was again using rainfall runoff model, and it's very practical when you have you don't have river flow data long enough to obtain an estimate of water resources availability, but you have rainfall data. So the idea is, let's start from rainfall to generate river flow. And basically what you need is rainfall data, and then you need some river flow data to perform the calibration, because we have seen that the rainfall runoff models needs to be calibrated. So this solution is then useful in this case. But in some cases, you have different kind of data available, and therefore, it's better to have a wide overview of all the possible solutions. The next solution is to use statistics. So to simulate synthetic data, another option is statistics. And I am aware that statistics is very often is a topic that is not really liked by students for many reasons, and also because it looks a bit complicated, and it looks very far from reality. And this is a feeling that I wouldn't like to give to you. I would like to show you, and with a preliminary discussion, and maybe with treatment of the topic that is more suited to our needs, I would like to show you that statistics is nothing else than a different view to look at processes. On the one hand, we have considered the rainfall runoff modeling, which is of course a solution that we can understand if we consider the physical process. Statistics is another way to look at the process, which may be, even in this case, physically based. So basically, what I would like to achieve with these lectures is just to show you that statistics is a very practical tool to solve our problem, which can be an alternative to rainfall runoff modeling. So what is statistics, basically? The definition of statistics is the science that deals with the collection and analysis of data. It's a science that deals with collection and analysis of data. Then I will give you a formal definition later on. But now let's just understand that it is nothing else than looking at the data and try to understand how the data behave, and trying to understand how, let's say, how frequent some events are. So this helps us, because in water resources assessment, we just need to understand what is water resources availability, and therefore how much often we have floods, how much often we have droughts, and basically what we would like to achieve is an understanding of the frequency of occurrence of particular situation. So we want to have a look, for instance, at the summer season, and to understand how much we get in trouble because we don't have enough water to irrigate or enough water to feed people, etc. So basically, what we need is indeed to look at the data and trying to understand the frequency of occurrence of such event. And therefore, it's the same purpose that statistics has. Look at the data and try to understand their behavior. In principle, statistics just looks at the data by ignoring the underlying process in principle, meaning that you can look at data of rainfall data or look at data like potato growth, and the tools are the same. So this gives the feeling that when using statistics you are forgetting the process and just look at the data. And this has induced what I would call as a misleading understanding of statistics, at least in hydrology, because in principle this is true. It's true that you just look at the data, but when you try to understand the data and you try to understand how the data behave, you can take into account the knowledge that you may have on the process. And this is very important to remember. So in principle it's true that you just look at the data, but in this process, along this process, you have the opportunity in statistics to incorporate any physical understanding of the process. So let's get rid of this false feeling that statistics is forgetting about the process. Statistics looks at the data, but you can take information on the process into account. And this is very important to remember. What is the main difference between a statistical description and a description like that is given by a rainfall runoff model? On the one hand, we considered so far rainfall runoff models. This is a type of description that is different by the description that is given by statistics. What is the difference? So let's say that statistics deals with statistical representation, of course, and if we want to provide a reply to the question, what is the type of description then that is given by rainfall runoff model, I would say that it's a deterministic representation. So now let's understand, first of all, the difference. The difference is that in the deterministic representation, you have a one-to-one correspondence between inputs and outputs, meaning that the same input for the same initial condition, so same starting point, let's say, always leads to the same output. So you have a one-to-one correspondence. If you get a rainfall series, a temperature series, and you get the same initial condition, if you apply twice a rainfall runoff model, you get the same output. There is, again, a one-to-one representation. This implies that you don't have any uncertainty. So given a rainfall series, you get a river flow output with no uncertainty. There is a one-to-one relationship. On the other hand, in statistics, you don't have a one-to-one relationship. Your output is uncertain, meaning that if you apply a statistical model twice, you get two different results, even if you start from the same point. So this is the basic difference. In the statistical representation, I anticipate a term that I will introduce later on. In the statistical representation, you have an uncertain output, which means that you don't have a unique output, but several possible outputs. And again, as I said, if you apply the model twice, you get two different replies. In the deterministic representation, let me repeat this, you have for any single input, you have a single output. Now, first let me clarify this difference from a philosophical point of view, because one may wonder, what is more appropriate for me? It's better for me to get a deterministic representation, to use deterministic representation in water resources modeling, or should I use a statistical representation? Okay, from a philosophic point of view, we should just wonder whether the process of river runoff, river flow formation is uncertain or not. So if the process is like let's suppose that we knew the process with any perfect detail, we knew the process completely. So if we are confident that by knowing every detail of the process, we can get to a fully deterministic representation, meaning no uncertainty, then the reply is the deterministic representation is more suitable for my needs. But is this true? Do you think that runoff formation is a completely deterministic process, or do you think that chance may come into play and in a way impact this process? And be careful, don't give me a reply, because the reply is this question, let's say, is the subject of a very vivid debate in the scientific community. So we are still wondering whether the rainfall runoff process is, or any hydrological process, is deterministic or is affected by some randomness. And let me give to you some examples to clarify the situation. If it is deterministic, it means that, again, for the same initial condition and the same inputs, you get the same output. If it is random, it may be, for instance, that once that a drop of rain lands over the earth, the path that the drop of rain follows to go downstream is a path that is driven by chance. Like, you know, sometimes you may have, for instance, think about a mountain divide. If you have a drop of rain that falls right on the divide, it may be just a matter of chance if the drop of rain goes in this direction or this direction. And this might be a matter of chance by principle. Like if you toss a coin, for instance, it's completely a matter of chance if you get an head rather than a cross. Tossing a coin at lancio una moneta in Italy. So it's completely a matter of chance. But on the other hand, there are some people who reply that it's not chance. When you toss a coin, there are people who say, if I were able to completely represent the process, knowing the amount of the strength with which you toss the coin, knowing perfectly the coin, where is the center of gravity, and knowing perfectly the surface where the coin falls, there are people who say, I could describe deterministically the process. Actually, this is not possible. But in principle, there are some people who say, if I knew everything and I had a description that is microscopically correct, I could describe the process of tossing a coin. So these people say, if I knew everything on my watershed, I could describe deterministically what happens. There are other people, including myself, who are convinced that this is not the case. I'm not saying it is not possible. For sure it is not possible. Given our current knowledge, we cannot describe deterministically the tossing of a coin or the rainfall runoff process. But I'm saying that even in principle, even in the future, it will never be possible to describe deterministically the tossing of a coin or a rainfall runoff process. Because I say that the process is inherently random. So if you accept this idea, then of course the statistical representation is what you're looking for. And the statistical representation is what you're looking for, even if you were convinced that in principle it could be possible to use a deterministic representation, but in practice it is not. Because we don't have enough computing power, we don't have enough opportunities to describe microscopically the catchment. So, this is the difference. So if you accept the idea that deterministic representation is possible, of course you can get it. Otherwise, the statistical representation is the more appropriate. There is not much difference between the two. The big difference is that uncertainty here is taken into account. In any case, as I said, in practice, hydrology is uncertain because at least we don't have the capability to describe everything, and therefore, in any case, I think the statistical representation would be more appropriate. But of course, depending on your needs, it is also, in some cases, very useful to use the deterministic representation. And you should be aware that when you use the deterministic representation, you cannot take uncertainty into account. This is a fundamental issue that should be always considered. So now, given that we have this opportunity to use a statistical representation, and given that in many cases we may be convinced that this is the most useful representation, let's try to understand some more. First of all, there is a but, or a cons. People say in English, pros and cons, advantages and disadvantages. Because of course, if the situation was just like that I described so far, one would say, okay, why not use then always a statistical representation? You said that it allows to take uncertainty into account. You said that it allows to take into account our physical knowledge of the process, so why not? So why did you start with the deterministic representation and why didn't you jump soon to the statistical one? Because, you know, the statistical representation is quite hard to apply in hydrology, because we will see that the assumptions that we need to introduce to justify a statistical model very often are not met. So some people say, okay, that's fine, but you know, it's not so easy. And it's understandable that it's not so easy, because you are not just describing the process like in deterministic representation. You want to describe the process and represent uncertainty. So this is one more step. So you can understand that this is really difficult. But this is the problem. The big but is very often statistical models don't work really well. So some people say, okay, let me use the deterministic one. I'm not modeling uncertainty, but in any case, I give an indication that is useful, while the statistical representation may be so complicated to get that at the end is not really useful. Okay, now let's try to learn some more. And of course, learning statistics means learning how to look at data and how to understand regularities of data. So this is basically what statistics aims to do. In the deterministic representation, you aim to reproduce with a mathematical model what's occurring in nature. So you observe the catchment, and your aim is, let me try with a mathematical model to try to see what's going on, simulating reality with a mathematical model. Here, in principle, you look at numbers and try to identify regularities, meaning that, for instance, you look at numbers and you see that there is a seasonal signal. You see that river flow are higher, for instance, here in May, June, and October. And then when you simulate data, when you produce synthetic data, you try to reproduce these regularities. So basically, this is what statistics does. Look at the data and try to see regularities, or patterns are also called. And of course, I talked about seasonality, which is a simple example, but there are more complicated regularities or patterns that you may try to identify. And in doing so, of course, you look at the physical process. So for seasonality, for instance, I assume already at the beginning that I have seasonality, and I jump to estimating seasonality of the data. I don't need, when I look to river flow series, I don't need to assess whether seasonality is present. I know that it's present, I jump directly to estimating it. So this is the use of the physical knowledge. But from a practical point of view, what statistics does is look at the data and try to understand regularities. How can we understand the regularities? And Basically, the idea is to look at the frequency of occurrence of the data, frequency of occurrence of situations. How much likely is a particular situation? So I understand, for instance, that an high flow is more likely in October and in May and June. And I understand that a drought is more likely in summer. So I look at the frequency of occurrence. This is the trick. And I try to model with an analytical relationship this frequency of occurrence. And then people started to develop theories to do that, to look at the frequency of occurrence. And now let me start with the slides. Okay, so first of all, let me say that the opposite of a deterministic growth, deterministic representation deals with deterministic processes. So deterministic process, and deterministic process again is a process where you have a one-to-one correspondence between process input and process output. The process is, let's define the process as a natural phenomenon, an hydrological phenomenon that we want to model. And then the opposite is a random process. Not the opposite, let's say the statistical counterpart is a random process. Random means that it's driven by chance. And of course, in the chance, there are some regularities. And these are the regularities that we want to decipher with the statistical representation. Let's say, let me give you an example of regularity in the chance, which is very simple. If you toss a coin, and this experiment was done by a famous statistician, was Pearson. He just thrown a coin 24,000 times, and he got head for like 12,000 plus 17, which means that in the chance there is a strong regularity. When you toss a coin, if you make just a few experiments, like 20, you will see that you get a number very close to 50% of heads, which means that in the chance you have regularities, indeed. This is a simple example, but there are also other cases of regularity in chance that I will explain to you later, which means that chance is not really something which is unpredictable. It's unpredictable if you want to give a number, but the general behavior is very predictable. So if you toss a coin, it's impossible to predict what will be the results of the next trial. But the general behavior is very predictable. I may say that if you toss 20 times, then you get very close to 50% numbers in occurrences of heads, which means that chance, it's not exactly predictable, but the general behavior are. Okay. So statistics deal with random processes, and let me now introduce another word, which is stochastic processes. You can use stochastic as a synonym as random processes. And I'm introducing this term because this is very commonly used. There are many different definitions for stochastic processes. Let me define it like just a synonym of random process. Okay? And Now, the process is, as I said, the underlying phenomena that we want to model, and we use the term process also to identify the mathematical model, so the statistical model. So it can be used, strictly speaking, the process would be the mathematical representation of the natural phenomena. But we can use also the term process to identify the natural phenomena. Also in scientific publishing, they are used interchangeably. And what is a realization of a stochastic process, of a random process? The realization is the outcome. So what we observe in nature is a realization. If you take a time series of river flows, this is, if we assume that the river flow is a stochastic process, then the time series that we have is a realization. And keep in mind that a stochastic process may have several realizations, several possible realizations, because I said that the output is not unique. So basically, the assumption is that what we observe in nature is just one single realization of the mathematical statistical model that we use to generate it. But if we try again to generate again the process, then we get different outcomes and therefore several realizations. And what is the realization of the stochastic process? Is a time series. A time series is just a collection of variables, random variables that depend on time, like river flows. These are just definitions. They are not really important, so don't get trapped in definition. Just try to keep in mind what is the process. The process is river flow. We want to describe it statistically, which means that what we observe is just one realization of what our mathematical model can give us. Okay, now, be careful. Nature, what we observe, is not stochastic. This is quite a philosophical consideration. I make this consideration because I like it, but I won't ask you at the exam definition like this, and not this one in particular. I just want to make you aware what is the difference between what we observe and what we model. So in the deterministic representation, what we model is an approximation of what we observe. In the statistical representation, what we model is basically a general underlying process which is stochastic or statistical or random, which can give different outputs. One of these outputs is what we observe. But don't make confusion. Nature is really, we cannot say that nature is stochastic, because nature happens just one time. So for instance, our personal life is not stochastic, it's just one. So there are not several replicas, unfortunately, of our life. We cannot go back and live again and see what happens if we make different choices in our life. We have just an opportunity. We take our decisions, we make our experiences, and these are not random, you know, because the decision that we take is one and is that one. So when we decide what kind of university we attend, we make one decision, and it's that one, which is deterministic, really. It's precise. We cannot go back to the age of 19 and make the decision again and check what happens in our life if we take a different faculty. So basically, the process, the mathematical model that we use to represent the river flow is stochastic. So if we could make a mathematical model of our life, we could make it stochastic, meaning, and what is the usefulness of making it stochastic? We can simulate what happens if we select the faculty of engineering rather than the faculty of medicine, rather than the faculty of agriculture, and then we look at the different realization of our lives, of our life, and then at the end we can make some considerations. So this is the usefulness of a statistical representation, which allows us to consider uncertainty. When you have to select your faculty, you are uncertain. Sometimes And therefore, with the statistical representation, you could make a simulation that allows you to see what is the effect of uncertainty. But indeed, what happens in your life is just one choice, and it's not stochastic because, you know, choice is done just once. And these are, again, philosophical considerations. I just want to you to understand what is the meaning of uncertainty, and in the case of our life, uncertainty gives rise to different trajectories. Like in the river flows, uncertainty gives rise to different trajectories, and a stochastic representation allows you to see the effect of the different trajectories. So at the end, you may realize, for instance, that in your life doesn't make a big difference if you select the faculty of agriculture rather than the faculty of engineering. This is the usefulness. But at the end, you have only one opportunity. And then let me see. When you compute, when you see a time series of data, there are some quantities that you may compute which are called statistics, like the mean, the standard deviation. I will introduce these statistics later on. These are usually quantities that you already know from your experience, because it happens frequently that you compute the average of a variable, and usually this is done because this variable is uncertain, and then by computing the average, you want to get an idea of the mean value that this value may take, this variable may take. Like, for instance, if you get river flows in a river, very often one computes the average because it gives an indication. You are uncertain about the future values of the river flow, and therefore you compute the average because it gives you an indication of the most likely value. This is common in our life. Like if you go to the bus stop and you see that the bus is not really on time, then people usually make statistics and compute the average and say, okay, the bus on average is 10 minutes late. So you get an indication in the presence of uncertainty for telling other people how long they can wait for you. This is quite common in our life. Okay, please note that in doing so, you are using statistics implicitly. And this computation on uncertain values that a variable may take, this computation, you are using them because you are uncertain, and you use statistics to quantify this uncertainty, to describe the processes in uncertain terms. So what I call statistics of a time series or a process, like mean, standard deviation, are quantities that you already know, that you currently use in your life, but they come from statistics to help you to quantify uncertainty. Okay. Now, this is the definition. Statistics is the science of the collection, organization, and interpretation of data. There is an off which is missing here. It deals with all aspects of this, including the planning of data collection in terms of the design of surveys and experiments. Okay, interpretation. This is when I said sorry, that we try to estimate regularities or patterns. This is interpretation of data. And again, interpretation means that you take your knowledge into account, physical knowledge. Now, as I said, there is one way to get an interpretation of data, which is looking at the frequency of occurrence of data. And to look at the frequency of occurrence, in general, to get an interpretation of data, then you have another science that comes into play, which is probability. So probability is something different from statistics. Statistics in general is the science of collection, organization, and interpretation of data. Probability is a way of expressing knowledge or belief that an event will occur or has occurred. Probability theory is used in statistics. So probability is a theory, sorry, not a science, it's a theory. So a collection a theory basically is a collection of definitions, theorems, and methods, let's say, that allow us to express knowledge or belief that an event will occur. Like, you know, now we are used to make probabilistic statements on the outcome of the elections. And this is probability, so basically you try to estimate how much likely is to elect President of the Republic Napolitano as it occurred, and you wouldn't say before that it was likely, that it was highly probable, but it occurred. So basically probability is a way to make, to assess the frequency of occurrence of an event, which means to assess knowledge or belief that an event is likely. Now, what is the definition of probability? Because if probability is a way to express our belief that an event may occur, like our belief that a drought may occur in May, how can we express it? Let's provide now a mathematical definition. What is the probability of an event? Of course we know what is, at least in concept. We know what it means to say that an event is probable or not. Of course we know that. But mathematically, how can we define it? So first of all, let's say that we don't have a unique definition for probability. And we don't have really, what I mean to say is that we don't have the opportunity to define in a direct way and consistently what probability is. So if you say, for instance, I think it's likely that tomorrow it will rain, if you give me if I asked you to